All right, so let's continue. This is the third part of the lecture um, on path integrals and Feynman diagrams. Now, so I want to discuss how we go beyond Gaussian integration. And when you go beyond Gaussian integration, which is exponential of a quadratic term, that means that we're going to now introduce something beyond the quadratic term in the exponential. And that the simplest thing to put there would be a cubic polynomial. And the idea here is, again, going back to the first lecture, that the quadratic term should represent the kinetic energy of a particle under no forces, and then the higher degree part, the cubic term, we are going to interpret that as if that was coming from the potential in the Lagrangian, and so the action has this kinetic and potential part, right? Now, what I'm going to do is I'm going to describe this in dimension 1, and then after I do the dimension 1 case, I'm going to do the dimension n case. So let's start with the one-dimensional case. So going back to dimension 1, imagine that that I want to compute the expectation value of a monomial of degree 2n. So this is by definition the integral of x to the 2n times e to the minus 1/2 a x squared. And this is going to be normalized by dividing by this Gaussian integral. Okay. And remember that the argument that we went through was that we were going to do this in the following way. We're going to add a source term, and we're going to replace this polynomial in front by d by dj to the 2n acting on this modified term. And this will just remain the same. And of course, this is del j to the 2n applied to e to the, let me put it this way, 1/2 a inverse j squared. Okay, and then we're going to set j equals 0. Okay, and we saw that one way to determine this is to do a diagrammatic calculation. We're going to have 2n dots, and they will all represent x. In the higher dimensional case, we had x1, x2, up to x2n. But here, because we have only one variable, and we're going to compute expectation value of 2n power, it's useful to kind of break it up into 2n copies. Another way that people sometimes denote this is by just labeling 2n, that we really only have one variable x, and we have 2n legs coming out of it. And now what we need to do is we need to pair these together. Okay, so the idea is that the reason that these pairings are coming is that these operators pair up, and the motto is you bring down a j and I'll kill it. And in this way, every time that we have a pairing, we get a factor of A inverse. Okay, and so the conclusion is that the expectation value of x to the 2n will be, so we're going to have the sum over all pairings of 2n positions each pairing will contribute an A inverse, so there will be n copies of A inverse. Okay, and so therefore it will be A inverse to the power n times the number of pairings. So just as an aside, how do we compute the number of pairings, which are basically partitions of 1 up to 2n into pairs? How do we compute this? Well, the way you should compute such things is by figuring out so the way you should compute it is in the following way. So we choose one of these partitions. So let me draw one of these partitions. If I pair 1 and 2, 3 and 4, and 2n minus 1, 2n minus 1 and 2n. So if I pair them all in a row, so if I do this, which pairs them just in a straight line like this, that is one of the partitions. Okay, and it's clear that the permutation group S2n acts transitively on these partitions. Because if I relabel 1, 2, 3, 4, up to 2n, if I relabel them, then I will get another partition of the numbers from 1 to 2n. And any partition into pairs can be obtained by this action of S2n. So S2n is let's give this this a name. So this is the cardinality of the set of these partitions into pairs, and S2n acts transitively on the set of these partitions. And what is the stabilizer of one of these partitions? This particular one. Well, in order to preserve this partition, certainly what I could do is I could switch 1 and 2, or 3 and 4, or any successive pair, odd, even. If I switch them, I will have the same pairing. So so there's definitely an S2 for each pair. So there's an S2 to the n. S2 is the just Z mod 2Z. It's a group of 2 elements. So these are just switching 1, 2, or 3, 4, etc. Okay. But that's not the only thing that you could do. What you could do also is send you could send the entire pair 1, 2 to the pair 3, 4. Okay, so in other words, if you could permute the paired elements, so we could take the product with Sn, and this one is taking 1, 2 and switching with 3, 4. Well, these are not switches, but these are kind of permuting the paired the pairs. Okay, and so what this means is that the number of such pairings is equal to 2n factorial, the size, maybe I'll just write it out first abstractly. So the cardinality of S2n divided by the size of the stabilizer, the cardinality of S2 times the cardinality of Sn. And this is exactly 2n factorial divided by 2 to the n times n factorial. So what we get is that x to the 2n is a inverse to the 2n, n times 2n factorial over 2 to the n times n factorial. Okay. This is just, if you want, this is just a warm-up. I'm back in dimension 1. Okay, now I want to introduce interactions. So just keep this in mind. We now introduce interactions. So what is it? What do I mean by that? Well, I'm going to compute now let's suppose that I want to compute the following. So so this is the original, which we could call the free action. And I'm going to add to this a cubic term. Sometimes it's useful to put a numerical factor in front of the b, but for now, let me not do that. Okay, and suppose that I wanted to compute this integral. Oops. And let's say I normalize it by the free action. Okay, suppose this is what I want to compute. Okay, and the jargon is that this is the interaction term, and this b is the coupling constant. And we're going to view this as a small parameter. Okay, so we're going to try to do perturbation theory. So the idea is we're going to do perturbation theory with b as small parameter. Okay, so let's try to do that. So what's the idea? How do we implement this idea? We're going to Taylor expand e to the bx cubed in this way. And what we see, the result, okay, is very nice. It looks like this. I'll put the result on the next page. The result of doing this expansion is that we get okay, and notice what we have here is each term is an expectation value. So this is 1 plus so you see that we get a power series in B. Okay, because each one of these terms is just exactly like this. let's see, what we have is a polynomial times a Gaussian integral. So notice that we have odd powers here, and that because this is pairings, because we need this idea of pairings, the odd powers are giving a 0 answer. So the odd terms don't contribute. We only get the even terms. And we have an explicit answer. So let's write this as a sum over b to the 2n, x to the 2n over 2n factorial, where n is going from 0 to infinity. So I got all the even terms. And this quantity is equal to 2n factorial over 2 to the n factorial, which is what we just did up here. Oh, excuse me, and I'm forgetting the a inverse to the n. So what we end up with oops, sorry, I made a mistake here. This here is 3 times 2. So this should not be 2n, it should be 3n. Let's do that again. This should be 3n. No, sorry, 6n. Well, maybe I'll write it in a slightly better way. So this is x cubed to the 2n. Okay, and let's do it properly now. So this is x sorry, 3n okay, and so what plays the role of n in this formula is actually 3n downstairs. So everything here should be n should be replaced with 3n. So we get a inverse to the 3n. We get 6n factorial over 2 to the 3n times 3n factorial. So in the end, we get okay. Now, so this is giving us our answer. This is the this is a perturbative series where b is the small parameter. Now, when you have all these expressions, it's kind of hard. It's kind of hard to see how this thing is growing. So but I think that you should be able to convince yourself. Here's an exercise. Use Stirling's formula Stirling's formula says that n factorial behaves like square root 2 pi n times n to the power n. Use this to show that this series is divergent. In fact, the coefficients, I believe, go like roughly like n factorial. The numerical coefficients, I mean. So this thing has radius of convergence 0. Okay, but okay, so I want to make two comments about this. So first comment is that I want to address why the formula is divergent. I'm not going to tell you why it's divergent, but I want to say something about the fact that it is divergent. So look at the integral that we are trying to compute. Don't worry about this. This we computed. It's just a constant. It's just square root pi over a, square root 2 pi over a. This integral is the thing that we're trying to compute, and it appears to be problematic. Why? Well, okay, if the region of integration is from minus infinity to infinity, this free action is very well behaved. It vanishes. It becomes exponentially small as x goes to plus infinity or minus infinity. But what about this term? I mean, if b is positive, okay, then this becomes exponentially large and would dwarf this term in the exponential, right? I would have e to the bx cubed, where x is very large. That means this is very large and the exponential is even larger. So whether b is positive or negative, there will be a problem either at plus infinity or minus infinity. So it seems like this integral is not well defined. And so you might be tempted to think that the reason that this series is divergent is because the integral is not defined. But yeah, that's not correct. Let me explain why. So, but is the integral even defined? Okay. So, let's assume that b is positive, and we're trying to integrate e to the minus 1/2 ax squared plus bx cubed. So definitely from minus infinity to plus infinity, this is not going to work. So let's forget about that. And let's extend to the complex plane. So let's assume that now x is a complex variable. I just mean here that this is the x-plane, and here's the real axis. Okay, now when x is large, let's analyze this. So when x is large, in the sense of the complex plane, so it can be a large circle, suppose, then the cube of x may be, so for example, if I let x be large in the real direction, in the positive real direction, so in the r plus, so I'm not sure how to write this. So e to the bx cubed is huge when x goes to plus infinity along r, and is small as x goes to minus infinity along r. So in other words, in this region, the integrand is very well behaved. It vanishes exponentially. It becomes exponentially small. But in this direction, it's not good. It's growing without bound, exponentially quickly. Okay, so what happens if I start rotating by an angle theta? Then x is cubed, so that means that this angle will be, if you move up a certain angle, then it will be tripled. And so for x large, we have to look at the real part of x cubed. Okay, and what you see is that the real part of x cubed, so let's say if I look at a small angle, say theta, this would be 3 theta, and the real part is still positive. Okay, so that means that the bad region extends, the bad region extends up to this angle, and the same goes for the opposite direction. All right, now if if this is the imaginary axis, and if I trisect this angle, Okay, then if I go up to this angle, triple this angle will be exactly the imaginary axis, and the real part will be 0. So that means that this angle is special. This is the, pi over 6. And then there's another minus pi over 6. The reason that these directions are important is that it will be bad, the integrand will blow up to infinity as long as the angle lies within this sector. And as soon as we pass this sector, it will be good again. So here, okay, the when I take x cubed, it will be in the x cubed. If I take x here, then the cube will be somewhere around here, and it will have negative real part, and so the integrand will be exponentially small as x gets large. So so where does the good region extend to? Well, it's completely symmetrical. So what you have is that this will be a good sector. This will be a good sector. This will be a good sector. And this will be a bad sector. And this will be a bad sector. Okay. If we compare this picture with the picture for e to the minus, so just compare this picture to the picture for e to the minus 1/2 ax squared. Okay. We know that the good sector, when I say good and bad, I mean that good means that it's exponentially decaying at infinity. That will happen. So there are special angles here. This is pi over 4 and minus pi over 4. And what happened is that this whole sector is good. So in other words, if x goes to infinity in these directions, the integrand exponentially decays. And similarly back here. And these are bad regions. You can't go along the imaginary direction. Okay. So luckily, what we did before when we were computing the integral of the Gaussian was that we integrated along this contour. Okay, a contour which went to infinity in the good regions, and we got a good contour and a well-defined integral which actually had an analytical result, which was square root of 2 pi over a. Okay, and so what's happening in this case is that we cannot expect this contour to work. This contour is okay at this end, but is bad at this end. So this is completely the wrong contour to be using for this problem. Instead, we should be using a contour that looks something like this, say. Another option would be, this contour or this contour. There's several contours that we can choose. And if this was our contour C, then this integral would be well-defined. This integral would be well-defined just as the Gaussian is well-defined, and has a finite result. And then with this well-defined integral, we could make the same argument as before. We could treat B as a small parameter. We could expand in Taylor series. And then we would have the problem that and so we could try to make the argument work as before. And of course, there's an issue about using, the question is, in this argument, when we Taylor expand this function and we use this argument, the question is, what contour are we using in this computation? Well, as you can see, there is an overlap between this region and this region, right? So there is no contradiction. We could use the contour C, okay? And if we choose this contour C properly, like what I've drawn here, then the same contour would make this integral well-defined and this integral well-defined. And so there is no problem about the definition of these integrals, about the sum, about each summand in this infinite series. The problem is that it's the interchange of limits, right? I mean, I have a limit process happening here to define the function e to the bx cubed. Okay, and then I've taken this limit out of the integral and I have replaced it with this limit. Okay, so it's this exchange of limits which is not kosher. Nevertheless, this series is what I get at the end of this long computation. So in the end, what the situation that we're in is that we have a perfectly well-defined quantity. This, we have this integral, which is a perfectly well-defined quantity, and we have some kind of infinite series, some power series, divergent power series, which somehow represents it. Okay, now, this situation may seem bizarre, but it is a very common phenomenon, and it has a name. It's called asymptotics. It's called asymptotic series. So the answer to this puzzle is that when you do this non-kosher exchange of limits, what you obtain is not a convergent power series for this quantity, but it is an asymptotic series for this quantity in a certain sense. So why is this happening? So why are we obtaining an asymptotic series? And I'll try to explain briefly what an asymptotic series is. Why are we obtaining an asymptotic series for this quantity? Let me call this quantity f of b. For f of b, instead of a convergent power series. The answer is that f of b has an essential singularity at b equals 0. Okay, that is the reason. So if you try to expand it in power series about that point, you will fail. It doesn't have, it's not analytic at that point. It's analytic elsewhere, but it is not analytic at that point. And yeah, so it makes no sense to expect that we are going to get a convergent power series in B. Okay. So I just want to explain what the meaning of this asymptotic series is. So what is an asymptotic series? How does it approximate this f of b function? Okay, and yeah, sorry, I'm just hesitating about going in this direction because it's somewhat of a long aside, but I feel like it's important, so maybe it's important for you to see this at least once. So let me give an example. So this is an aside. Consider the integral f of x. I'm going to integrate from 0 to infinity. This is called a Stilts's integral. Okay, now what kind of a function is this? Well, the integration contour is just what it looks like. It's on the real axis from 0 to infinity, where this this part of the integrand is rapidly decaying. So yeah, no matter what the value of x is, okay, like if I'm trying to compute yeah, so let's say that x, if x is on the positive real axis, suppose, then this is a positive number. This is a positive number, this x. And since t is going from 0 to infinity, this denominator remains positive. Okay, and I'm integrating something that's exponentially decaying times this, this non-zero function, this well-defined function, and we get a well-defined answer. So this function is perfectly well-defined at this point. Okay, and this argument holds for any x, except there's a problem where, for example, if x is negative, so if x is somewhere here, suppose, okay, then this is a negative number, and there will be a positive value of t, okay, namely 1 over x, or minus 1 over x, okay, which will make this quantity minus 1, and this will be 0. And so then this integrand will blow up. So the idea is that, the way you should think is that we have the t-plane, and in the t-plane we have a contour, which is going off to infinity like this. This is the contour. Okay, and if x is a positive number. So here the pole in the t-plane occurs at t is minus 1 over x. So if x is at position 1, right, then minus 1 over x would occur here. And this pole doesn't interfere with the contour, right? And so, as I move this 1 up here, then this will move around here, and it's it's not interfering with the contour. The problem occurs with this red point in position 2. And so as soon as the point x is on the negative real axis, minus 1 over x is on the positive real axis. And this is now interfering with the contour. So as defined, f of x fails to be defined on the negative real axis. So I draw a squiggly line where f is undefined. Otherwise, f of x is analytic. So on this region here, f of x is analytic. Okay. So we know f is not analytic at 0, but let's expand anyway. Okay, let's do that expansion anyway. Let's do the non-kosher interchange of let's take this 1 plus xt, and let's expand this out. So this is equal to 1 minus xt plus or even let me write it this way. So the first term will be 1. The integral of e to the minus t, if I integrate e to the minus t from 0 to infinity, the integral of this will be minus e to the minus t. Evaluated at infinity, that will be 0 minus, so that will give me a 1. Okay. Then what I'll get here is 1 plus xt to the minus 2 e to the minus t. And I can continue this process. This is just integration by parts. Here I'm differentiating this differentiating this, and that's what's giving me the 1 plus xt to the minus 2. So if I continue this process of integration by parts, I'm going to continue in this way, and what I'll get is this series 1 minus x plus 2x squared minus 3 factorial x cubed minus 4 factorial x to the 4th plus minus 1 to the n minus 1 times n minus 1 factorial times x to the n minus 1 plus some error, or whatever the remaining terms are. And this error will be minus 1 to the n factorial, x to the n, integral from 0 to infinity of 1 plus xt to the minus n plus 1 e to the minus t dt. Okay, so what we see here is that I have a series expression with an error. So this is an exact equality once you take into account the error term and so on. So let's just see how we can interpret this series of equalities. So if we represent f of x by the series which is sum minus 1 okay, if we look at this series, then obviously this is a divergent series. Okay, so it seems like it would be useless to use this series to approximate the function f of x. Okay, however, on the other hand, the error after n terms is epsilon n, and the size of this error is what? Well, if we look at the expression for it, we have n factorial x to the n times something, which is an integral of this quantity here. Now, let's see. So let's assume that x is positive. Oops. If x is positive, then this quantity is bigger than 1. And so this integral is bigger than 1. Okay? So the error is bigger than, the error This integrand, 1 plus, so if you look at 1 plus xt, this part is bigger than 1, but this is a negative power. So this is 1 over something bigger than 1. So this is smaller than 1, and this integral is less than 1. So under this assumption, this thing is going to be less than 1. And so this is telling us that the error is less than n factorial x to the n. Okay, so look at the series. Okay, so these are n terms, 1, 2, 3, all the way to the nth term. And the error for the nth term is bounded by this quantity, and this quantity is actually the n plus first term. So the error is bounded by the next term in the series. Okay, so the so the point is that so if we are trying to evaluate f of x, for let's say for x equals 0.001, suppose. Okay, and suppose that this is the number of terms and this is the error. Okay, then look at how the error behaves. So the error is bounded by a product of these two quantities. Now, of course, as n increases, because x is very small, this x to the n is getting extremely small for large n. But this factor is becoming extremely large for large n. In fact, larger than x to the n, because n factorial, according to Stirling's formula, it's behaving kind of like n to the n times square root n. So, so this means that eventually this n factorial will dominate over x to the n. But it may take some time for that to happen. So the error is going to behave like this. It's going to something like this. So there will be a certain number of terms which is optimal. Okay, so if we're trying to evaluate f of x for x equals 0.001, we want to sum to so many terms so that we want to sum until the smallest term. Okay, and this is the best that we can do for this value of x. So every value of x will have its own ideal number of terms, and so this means that this is an approximation. It is a form of approximation. It's just not. It's not the type of thing where you can get arbitrary precision for a fixed value of x. Like if you fix x and you say, I need to evaluate this function f of x, I need to evaluate it at a specific x, there is a limited amount of precision that you could hope to get. And that is exactly summation until the least term. On the other hand, if I let x, if I let x get smaller and smaller, right? If I now ask the same question for x is 0.0001, okay, then this picture will get shifted this way, and I will get a better approximation by summing to that least term. Okay, so in that sense, if I allow myself to, if you want more precision, you have to ask the question for smaller x. That's the bizarre way in which asymptotic series work. So for a fixed value of x, there is a limited amount of precision that you can expect to get from this type of a series. So anyway, this is the meaning of asymptotic series. It's not like Taylor series. The error does not go to zero. It has a behavior somewhat like this. So I just wanted to point this out because what's really going on here, the thing that we're actually computing when we do these calculations, these series that we're getting, these perturbative series, they are asymptotic series for these integrals that I explained are well defined. Okay, now just a comment about this. So let me just write what I just said. So the perturbative series is in fact an asymptotic series for the path integral which is well defined in our case, in our simple case. Okay, but in quantum field theory, there is usually no analog of the good contour. And so there is no well-defined quantity to approximate. Nevertheless, we may obtain perturbative expansions using the Feynman diagram calculus. Okay, these power series, the resulting power series, are thought to be asymptotic series for the true path integral, but this is unknown. Okay. Freeman-Dyson tried for 4 years in the 40s to prove that the perturbative series of QED, quantum electrodynamics, converges. And he realized this is in a 2 or 3 page paper, which is a remarkable paper, that it doesn't. And so ever since that time, there has been, this mysterious situation in quantum field theory that the computations that are being done, even to this day, the most precise agreement between QFT, quantum field theory, and experiment, it comes from evaluating 6 or 7 or 8 terms of the perturbation series. Okay, and the meaning and the mathematical, so the status of the series as an asymptotic series for something is still unknown. Okay, so I think it's important for people to realize that the most precise results that we have comparing theory to experiment are as a result of expanding a few terms in a series, the meaning of which is completely unknown. So this is why physicists are so keen to find what they call non-perturbative definitions of QFTs. So they really would like to define QFTs in a way that did not rely on perturbation theory, and so maybe they could define what these path integrals are and show later that the perturbation series is an asymptotic expansion for it. Okay, this was just a long aside. And I wanted to make a second comment about this calculation, this result. So if we take another look at this result, I just wanted to point out that that you see it's true that okay, just imagine the diagrammatics that would be involved in drawing these pictures. So what we said before was that if you have x to the 2n, then you could think of it as just 2n copies of x, right? And that what we're doing is we're pairing these together, right? So each time that we compute, let's say, this x to the 6, we could imagine drawing 6 dots, right? So let me explain what I mean here. So you could imagine drawing for 1 over 2. So for the term 1 over 2 factorial b squared x to the 6th, right? You could draw it this way. Okay, and you would have to pair this together in all possible ways. Right? Okay, you could write it this way. And then and then if we had the next term would be 1 over 4 factorial b to the 4th x to the 12. So it's x cubed, 6, x 6th, and then 12. So then you could imagine, right? And then pairing all these together and so on. Okay, now I just want to point out that this is not the way that people draw these diagrams. Instead, they realize the following, that you see that the quantity that comes as one unit is bx cubed. This is always together. This is b squared x cubed squared, right? So what it means is that, because of the fact that we were doing an expansion of bx cubed, this quantity is always coming together as a single unit. And so what we'd like to do is just have a single diagrammatic piece corresponding to this basic element. So instead what we do is that we introduce a trivalent vertex like this. Okay. Since we introduce this to the diagrammatic calculus, because it always occurs in an independent way, or as an indivisible unit. Okay, so for example, so yeah, so what I want to say is that you know, for this term, what's happening is that we have two vertices, two of these B vertices. Let me see, how do I want to describe this? Okay, so the first non-trivial diagrams occur at order b squared. So I have two of these b's. Okay, and then I need to, and these two b's, they provide 6 points, right? Which is correct because I need to compute the expectation value for 6 points, right? And so the idea is that I need to now pair these together. This is one possible pairing. And every time I do a pairing, I'm going to have an A inverse. And there's a different way of pairing. I could pair, for example, in this way. Okay, and notice that the result of this pairing is a diagram that looks like this. Whereas the result of this pairing is a graph that looks like this. Okay, this is called a dumbbell graph, and this one is called a theta graph. Okay, so how many pairings do we have? Well, we already saw that when we're computing this x to the 6, right? We just have 6 dots. Oops. We just have 6 dots, and we're pairing 6 dots, and we basically have this calculation here for the number of pairings. Okay, but some of these pairings, so actually, how many pairings are there in this case? So in this case, we have the number of pairings is so this is for x to the 6, right? So it's going to be sorry, I'm forgetting. Oh, I see. Sorry, n is equal to 1. Oh, sorry, I'm getting confused because of this 6 power again. So n is equal to 1. I have two b's, b squared. So if n is equal to 1, I'm going to get the number of pairings will be 6 factorial over 2 to the 3 times 3 factorial. So the total number of pairings is 6 factorial over 2 to the 3 times 3 factorial, which is 6 15. So there are 15 pairings. Okay, and let's look at these 15 pairings. So yeah. So if we look at these pairings, right? Actually, let me just grab it from up there. Okay, just take a look at what these pairings would look like. So here is a dumbbell pairing, right? But there are other dumbbell pairings. I could do this, and that would still look like a dumbbell. Or I could do this, and this would still look like a dumbbell, right? And well, you can see that, you know, if you're going to make a dumbbell, then 2 of the 3 legs coming out of B must be paired to each other. And there are 3 ways of doing that. Okay? And for each one of these, there will be 3 possibilities of how to pair the other ones. So it's clear that I can, continue this. I can continue this pairing like this. I could just go here. This would be another one. And finally, this one, right? And so I could continue in this way. Oops, sorry. Right, and this would be, these would all be different pairings. And so I would get 9 dumbbell pairings. Okay, so of the 15 pairings, 9 of them give rise to dumbbells. The rest, i.e. 15 minus 9, 6 give theta graphs. Let's take a look at that. So I have my basic theta graph. And the key property of the theta graph is that every leg on the left is glued to a leg on the right. And, you know, if I look at the first leg on the left, where will it be sent? Here I sent it to the third. I could, of course, send it to the second, or I could send it to the first, right? And then leave, so, and then I could, you know, let's see. There's also this possibility where I let them cross. Or this possibility. Oops, sorry. Okay, so I have 6 pairings giving the theta graph. So just as a graph, that's what it looks like. Okay, so what we see is that there is a kind of classification of pairings which treats them a little bit differently. So there seem to be 2 types of pairings, 2 types of contributions to the to the first non-trivial term of the perturbation series. Okay, you could think of them as just 15 pairings, each contributing the same amount, or you could think of it as 2 types of graphs, 2 topologies of graphs, the dumbbell and the theta, but that the dumbbell and the theta are contributing different amounts. The dumbbell and the theta contribute with a ratio of 9:6. Okay, so there's a very beautiful combinatorial result, which is called Feynman's theorem. So okay, Feynman's theorem is a method for counting contributions, which focuses on the graph topology instead. On the graph topology. Okay, so let me explain that briefly. Okay, so okay. The reason that I'm hesitating is because there is a numerical factor issue, which I want to make sure I get right. So okay, so the theorem says the following. So let me just do it in this very simple case. Oh yeah, sorry. Okay. So let's say that we have this function. Let me see. Where S is going to be 1/2 ax squared and then I want sorry for the signs, I'm just trying to get the signs right, and this will be right, I believe, and I need a 3 factorial numerical factor x cubed. I'm not including the a dependence. Of course, this depends on a. Z depends on a as well, but I'll just consider a to be fixed, and b, the interaction term, the coupling constant, is the thing that's changing. The reason that I put this minus sign is so that it becomes positive in the integrand, and I don't have any signs when I expand. And the reason for this 3 factorial is that it's conventional in the statement of the theorem, of Feynman's theorem, to put the interaction term with the power as the factorial here. So let me just, that will avoid having other factors showing up later on. So the theorem is that Z of B is the free result, Z of 0, whatever that is. We know what it is in our case. It's going to be square root 2 pi over A, but never mind. It's just Z0 times a sum, okay, over Feynman graphs gamma. Okay, and there is a factor of 1 over the automorphism of the graph, the size of the automorphism group, okay, multiplied by, there's going to be B, and there will be factors of A inverse, okay? And the number of B's will be the number of vertices, and the number of A's will be the number of edges. V is equal to the number of vertices, and E is the number of edges. Okay, so this is a different way of counting. It's it's giving the same result as the result we had above. This will be the correct result, but it's expressed now in terms of a sum over graphs. So I need to explain, so this is a much more efficient way in some cases to obtain the result. So I need to explain, first of all, what is a Feynman graph and what is its automorphism group. So a Feynman graph, okay, it may seem a little strange, but this is what is needed. So a Feynman graph is a set H of half edges with two partitions. Okay, number one, it's the partition into edges. These are sets of size exactly 2. Two half edges make a single edge. And 2 vertices, sets of size 3 in our case. We could have interaction terms like c to cx to the fourth, in which case we would have different types of vertices, ones that would be labeled by B, which have valency 3, and ones that would be labeled by C, which have valency 4. Valence 3 or valence 4. Okay, and an automorphism of gamma is just a bijection which preserves the partitions. Okay, so let me give some examples. Okay, so suppose that I have, suppose that I look at, just as I was doing before, let's say that we had, well, okay, let's look at a, let's look at a case with 2 vertices. So what are the vertices? Well, the vertices are collections of size 3, of half edges. So I've drawn here the partition. I don't know, I guess maybe it's useful to start from scratch. So it's like, imagine that we have 6 half edges right? And this partition, these are the vertices. And then these are the edges. Okay. The way that we normally draw such a picture would be like this. We have 6 half edges, and we're going to consider this collection of 3 half edges to be one vertex, this to be another vertex, and then what we'll do is we'll join these together to make a full edge. Okay. So this is a single Feynman graph, which is the theta graph. Okay, an alternative would be to let to let these be edges and the same vertices. So partition of 3, partition of 3, partitions of 2. Okay, and the way we would normally draw this would be to draw our two vertices again, and now we join like this. So we would get the dumbbell graph. Okay, so you can see how the Feynman diagram is defined like this. And I don't know, I mean, you could draw any trivalent graph like this. All right, and so you see that we have six vertices and 9 edges. And you know, the number of half edges, I'll just indicate them here. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there are 18 half edges. 6 vertices. And 9 edges. Okay, now let's look at automorphisms. So if I wanted to compute automorphism of the theta graph, suppose, then we have to consider what did I do before? Oh yeah. Right? So I'm going to consider now permutations of 6 half edges, but the permutations must respect the partitions, right? So so how many automorphisms are there for this theta graph? Well, one thing that I can do is I can just flip along this axis. So I would have an S2, which just flips the 2 vertices and sends each edge to itself. Okay, another thing that I can do is I can permute the 3 edges without changing the vertices. So I can, there's an S3 action on the edges. Okay, so you can see that these are, this S2 and this S3, they're both sitting inside the S6 of permutations of all the half edges. But the point is that these are the ones that respect the partitions. So the automorphism group is, I'm not clear now on whether, to me it looks like a direct product. So this is just S2 cross S3. And the size of the automorphism group is 2 times 3 factorial, which is 12. Okay, now let's look at the dumbbell graph. Well, so I'm looking at, again, a permutation group on 6 half edges. Now, if I leave the vertices alone, then I can flip. There's an S2 flipping these 2 half edges, and there's another S2 flipping these 2 half edges. Okay, and then if I allow myself to change the vertices, there will be a flip this way, flipping the vertices. So in the end, what I get is S2 to the power 3, and the size is 8. So according to the Feynman theorem, I obtain this result. For the theta graph, I have 2 vertices, so 2 factors of B, and 3 edges, 3 factors of A, and then 1 over 12 for the automorphism group. And then I get, this is for the theta graph, and the next contribution would be 1 over 8. Again, there are 2 vertices and 3 edges. So in the end, I get what is it? What is it, 5 over 24? 5 over 24 b squared e to the minus 3. So we know, if we wanted to continue this, we know that So what would be the next term? We know that we would have, well, we can't have just 3 B's because the total number of edges is odd. And so this will have a 0 contribution. There are no graphs with 3 vertices. There are no trivalent graph with only 3 vertices. So I need a 4th one, okay? And so the next term, right, and so we need to consider diagrams that include 4 vertices. So, for example, this one would be one of them. But of course, we also have this one. And so there are going to be a bunch of contributions, and we need to figure out the automorphism groups of these. And so the question on the assignment, the last question on the assignment, is really trying to implement this. And I should also say that the proof of Feynman's theorem is a relatively simple combinatorial recounting, right? You're just counting in terms of graph topology rather than in terms of pairings of a fixed number of points. Okay, I hope that that is enough to go on for the last question of the assignment. And I hope it clarifies somehow the kind of crazy state of affairs that we have now in physics, especially when it comes to perturbation theory and the meaning of the perturbation expansion. Okay.